So we're going to spend quite a lot of time talking about matching problems. We're normally going to talk about them in terms of job allocations. There's many other kinds of problems that are mathematically equivalent to that, but job allocations is kind of quite an easy example to talk about. So here, this page is showing us various different ways to represent a job allocation problem. So here we've got 5 people, Anne, Bob, Kath, Dave and Ella, and we've got 5 jobs. There's a librarian, a musician, a nurse, optician, pilot. And various different people are qualified for different jobs. And so we need some way of representing information about which people are qualified for which jobs. And there's several ways to do that. One way is this so-called chessboard diagram we've got here. So the white squares correspond to cases where the person is qualified for the job, and black squares to the cases where the person is not qualified. So for here, for example, in the B, N position, that's a white square because Bob is qualified to be a nurse. Next to it, in the BM position, well, Bob is not qualified to be a musician, so that square is black. And similarly down here, Dave is qualified to be a musician, a nurse, an optician, or a pilot, so all these squares are white. But this square is black because Dave is not qualified to be a librarian. So each row represents the jobs that a particular person is qualified for. Dave is qualified for these 4 jobs here. Each column represents the people that are qualified to do a particular job. So this first column here is all the people who are qualified to be a librarian. This second picture over here, this is basically the same as the chessboard diagram. This is called the Incidence Matrix. It's just that everywhere where we have a white square in the chessboard diagram, we have a 1 in the Incidence Matrix. And everywhere where we have a black square in the chessboard diagram, we have a 0 in the Incidence Matrix. So it can be useful to do this as a matrix because there's some kinds of applications where you can do kind of matrix algebra, multiplying matrices or inverting them and so on to do various things to do with the matching problem. Another way that we can represent the information is just by listing the row sets and the column sets. So over here we have you've got these column sets which are written C, and you can think of C as column or C as candidate, right? So CL is the candidates to be a librarian. That's all the people who are qualified to be a librarian. That's all the people who are white square in the first column. Okay, so Anne, Bob, Kath and Ella, they're all qualified to be a librarian as listed in this column here. And down here, the people who are qualified to be a pilot. Anne, Dave and Ella are qualified to be pilots, corresponding to the white squares in the last column, or to the 1s in the last column of the incidence matrix. Alternatively, instead of listing the column sets, we can list the row sets, which you can also think of R as standing as role. So RA is the possible roles for person A, who is Anne. So Anne is qualified to be a librarian, a musician, or a pilot. So RA, the roles for A, is L, M, and P. Similarly, Ella is qualified to be a librarian, optician, or a pilot. So RE, the row set or role set for Ella, consists of L, O, and P for librarian, optician, and pilot. And notice, given any one of these 4 things, you can read off the other ones, right? If we know the row sets, okay, so we know the row sets, then we know what jobs Anne's qualified to do and what jobs Bob's qualified to do, and so on. From that, we can work out what the candidate sets are, right? I mean, if we want to find out the candidates for a librarian, we just have to look at which people have an L in their role set. So Anne does, and Bob does, and Kath does, and Ella does. So Anne, Bob, Kath, and Ella, those are the people who are qualified to be a librarian. In other words, the candidate set for librarian is A, B, C, E. So if we know the role sets, then we can work out the candidate sets. If we know the candidate sets, we can work out the role sets. And then yet another way to represent the same information is we can draw this so-called incidence graph over here. Okay, so here in the incidence graph, we've got a circle for each person, a red circle. There's a circle for Anne, for Bob, for Kath, for Dave, for Ella, and we've got a blue square for each job.
for librarian, musician, nurse, optician, pilot. And we have a a green line between the circle and the square when the corresponding person is qualified for the corresponding job. So Dave is qualified to be a musician, so we have a line between D and M. Dave is not qualified to be a librarian because this square here is black, so we have no line from D down to L. Yeah. So again, so each line here, it corresponds to a white square in the chessboard diagram, or to a 1 in the incidence matrix, or a line from D to N gives us an N in the set RD, or equally a D in the set CN. Okay, so when we've got a job allocation problem like this, we want to solve it. To solve it means we want to allocate each job to a person, and we want to do that in such a way that every job gets allocated to someone, and no job gets allocated to more than one person, no person gets more than one job. And one way to do it is like this. So we've indicated the solution by, we can do it by putting rooks in the chessboard diagram. Okay, so we put a rook in the AM position, meaning that we're going to let Anne be the musician. We put a rook in the BN position, saying we're going to let Bob be the nurse. And here, this rook here in CL means that Kath's going to be the librarian, and Dave's going to be the pilot, and Ella is going to be the optician. And notice, we've only got one rook in each row. Well, you've got at least one rook in each row, which means that every person gets a job. We've got at most one rook in each row. That means that no person gets more than one job. We've got a rook in each column, which means that each job gets allocated to someone. And we've only got one rook in each column. That means that we never assign two different people to the same job. And notice, the reason why we use rooks for this, is because we have no two rooks in the same row. And that means that, according to the normal rules of chess, the rooks can't attack each other. And we have no two rooks in the same columns. Okay, that means that the rooks can't attack each other vertically. That's why it's natural to use rooks. In terms of the role sets, what we've done is we've chosen exactly one role for each person. So for each of these row sets, role sets, we've picked out one entry. And we've made sure that the entries that we're picking are distinct. Okay, so picking out one entry in each role set means that we put a rook in every row, precisely one rook in every row, and we never mark the same element in two different row sets. That's the same as saying that we never have two rooks in the same column. Similarly, we can look at it from the other point of view. We can look at each job, and then for each job we've allocated one person to do it. So we choose one element of each of these sets, and we never choose the same element in two different sets, right? If we chose an A here and an A here, that would be the same as kind of saying that Anne has to be the librarian and the musician, and that's not allowed. Every one person is supposed to get precisely one job. And then in terms of the incidence matrix, what we've done is we've coloured some of these edges orange for the cases where we're assigning a particular job, right? We've assigned the musician job to Anne, so we have an orange edge between A and M. We've assigned the pilot job to Dave, so we've got an orange edge between P and D. And so the fact that every person gets a job, that means that every circle has one orange edge attached to it. And precisely one orange edge, because every person gets precisely one job. And the fact that every job gets assigned to precisely one person, that means that for every one of these blue squares has precisely one orange edge attached to it. And because of this kind of precisely one thing, that means that these orange edges, they're disjoint. If they touched at the round end, that would mean that you were giving the same person two jobs. If they touched at the square end, that would mean that you are assigning the same job to more than one person. So they can't touch at either end, so the orange edges are disjoint.